Today we would be doing the chapter 6, which is in fact application of differentiation. So first of all, we have to see what is a differentiation. Do you know what is a differentiation?
dy by dx.
Yeah, dy by dx, and right. But what is it actually in physical term?
It's
So first,
on
so
the
you
graph,
said dy by
the,
dx.
yep,
So yeah,
the gradient.
this is a
So,
gradient, right? This is
yep,
gradient, right, Becky? Gradient. And what is a gradient actually? And we also say if it is a linear graph. Linear graph means like this. Yeah. So what is this gradient means?
the gradient is rise over run.
Okay, that is rise over run. One way of saying is rise over run. And
The rate that it changes.
very nice, very nice. It's a rate at which changes. Why? Because it says if the run is 1, how much is the rise? Because you remember? So this means it is also a rate of change. Why? If we say if we say kilometer per hour, a speed, we say speed is kilometer per hour, right?
Mhm.
So it means how many kilometer at 1 hour. So
And
it means run is 1 hour and the rise would be the kilometer. So I mean, I would say distance on this and
mhm.
time in hour here. So it is in hour and distance is in kilometer. Do you understand that?
Yep.
That's interesting. So there are two things. So it means um, differentiation gives you the rate of change. Do you understand that? Hello?
Hello. Yep.
Yeah. Okay, let me ask you a little tricky question now. Let's say it's not a linear equation like this, rather something like a non-linear. It may be a exponential type of a thing. And then we
Mm.
see the rate of change. So if I put it here, the rate of change at this point, I mean this is at x if this is at x1, right? Or just at this place. And then there is another point here, which I say this point. And here I put, and I again draw a line here. So what do you think where the rate of change is higher, at point A
Uh,
or at point B?
point B.
Yeah, very nice. Point B it is because it's so if we are given the equation of this, let's say this red. I do not know what the equation is, but I can put like this just to make you understand. Let's say this equation is y is equal to x cube plus 2x square plus 3, right? I'm just
Mm.
making it myself. And I say A is 5 and B is 6. Can you tell me what is the gradient at 5? A is 5, A is 5, and B is 6. 6
Yep.
means X is 6, so we are having X, and this is Y. So I'm just making it myself. So can you tell me what would be the gradient at 5 and what would be the gradient at 6?
Uh, it will be the first we have to get the dy by
Yeah,
dx.
we would do that. We do it together. So dy by dx. Can you help me to write that?
3x squared
Very nice.
plus 4x
Yeah.
plus 3.
No,
No need
no,
to put.
because we understand. 3 means if I put like this is 3. Yeah.
Yeah,
And there is no variation. So rise over run would be 0.
0. Yep.
Yeah. Because y2 minus y1 is 0.
Hmm.
So this is now we have to find. So we would find the gradient, for example, at dy upon dx at x is equal to 5. And how we find that?
You substitute in 5 for x.
It's very nice. Plus 4x. 4 times 5. So this comes out to be something like 25 times 3 is 75 plus 20. So this comes out to be
9.
95. And if we put dy upon dx at x is equal to 6. So it gives us that. So it would be 3 times 6 square, sorry, it's not cube, it's square, plus 4 times 6. Yeah, so this
Yep.
becomes 3 times 36 plus 4 times 24. So you can tell me what is, I don't have a calculator. So 3 times
Uh,
36 plus 24. So that would be the gradient or rate of change at there.
132.
132, okay. So you understand. So this means we are now good to do exercise 6A. Yeah,
Yep.
I would try to be a little quick. Um, I would do this with your help. So let me know which question you want that we should attempt from exercise 6A. Have you done it in the class?
Yep. We finished chapter 6 by last week
Okay, okay.
after the test.
So
Yeah.
if you consider I can do one or two questions so that then we move um, to the exercise 6 to the next exercise then.
Yep. Following the survey of a particular mine, experts predict that with continued mining, the quantity T for tons of a particular ore remaining in the mine T years after the survey was carried out would approximately fit the mathematic model T equals 20T squared minus 420T, 20T cubed minus 420T squared minus 8,000T plus 150,000.
So I wrote that in the meantime, right? So
Yep.
this is, they say, what quantity of ore was in the time when t is equal to 0? Can you tell me that?
50, 150,000.
Yeah, very nice. So at t is equal to 0,
Yep.
t is actually 150,000. Yeah, that's good. Now the B part. What quantity of ore will be in mine when t is equal to 10? So what should we do?
We substitute T in
Yeah,
for,
t
for
equal to,
10.
yeah. So I don't do this. I mean, this is very obvious we would.
Yep.
Yeah. So we leave that. You we move to the third part. Find a rule for the rate of decrease of T in tons per year.
Is that dy by dx?
Yeah, dt upon dt.
dt.
Because
Okay.
it means we are asking dt
Yep.
upon dt. Do you
Yep.
understand that? Because it would be negative. It would become, because it says it is given to us. It says quantity of a particular ore mining remaining in the mine. So it would be going down. So can you
Mm-hmm.
help me write the derivation? This is the rate
Oh.
of change, and this time the rate of change is negative because if I plot like this, it would be something like this. It's going down
Yep.
quantity. Okay, help me to write.
6T squared
Good.
minus 840T
Yeah,
minus 8,000.
yeah, good. And because 150,000 is constant, so that would be zero. So we don't write that. We can do with just one part from D. It says find at any one of time. Which one you would like to see? dt
Uh,
at
Second part,
t is equal to 4. So,
4.
so you would put just how to do that?
You substitute in 4.
Yeah. Can you just do that so that we are able to check at the answer at the back? Just use your class pad. It would be how much? Negative
Negative 10,400.
10,400. Okay. Tons.
Yep.
And this should be, the unit should be like this per year. Why per year? If you see, it is t is 10 and time is in a year, so it is decreasing minus 10,400 tons per year. Is it
Yep.
good?
Yep.
Okay, we move to the next part because that is more tricky and we try to understand that. That is using differentiation to locate stationary point. Okay, um, so let me write that. It is using differentiation to find stationary point. What is meant by stationary point?
Uh, a specific point,
No.
a point where the gradient is equal to 0.
Yeah, stationary point means why it's called stationary actually. If you see here, I just make a graph maybe of a parabola which has actually moved, which is translated to a position, right? If
Yep.
you look at any point, the point, this point where is a stationary point. This is called a stationary point because here the dy upon dx, if it is y and this is x, so dy upon dx is 0. So any point where the gradient is 0. Why it's called stationary? We understand. Rise over run mean the
Yep.
rate of change. Once there is no rate of change, there is no change. So it means it's stationary. Do you understand why it's called stationary?
Yep.
Because we said rise over run. Rise over run means it has a gradient. The gradient is actually the rate, and the rate is a change per unit something. And if there is no change, gradient is 0, so it's a stationary point. Do you understand why it's called station? Dy upon dx is 0 and it's a
Mhm.
stationary point. Okay, so there are some uh, things where the point would be stationary, and I would draw them and then we would discuss them. For example, the first stationary point could be something like here. I'm sorry, it's not very well made. I just move that and I say like this. If I put here a line, so at this point you see it is a stationary point, right?
Yep.
And then I make another diagram like this. And here, again, and I draw at this point where I have put this is a stationary point, right?
Hmm.
Okay. These are two different type of graphs. The parabolas, it's a non-linear. It could be any equation, non-linear. So it could be parabola or other non-linear graphs. Do you understand this thing or no? What I say once
Yep.
I say non-linear. Actually, if you see y is equal to mx plus c, it is a linear graph. And in the linear graph, the highest power of x is 1. If you have any power more than 1, I mean, it could be x cube, x6, x3, they are all non-linear. And they would be having some type of these types of graphs where the rate of change would be varying. Do you understand this?
Yep.
Okay, this, if we look at this graph, this is a minimum point. Why? Because the graph, all other values are more than that. Do you understand that?
Mhm.
Okay, yeah, so minimum point. And this is a maximum point, right? We would first discuss these and then we would see. So can I change the color? Uh, what is dy upon dx here at this point?
Uh,
At this point,
0.
0, because there is this is a horizontal line, and we know if it is a horizontal line, y2 minus y1 is 0. Do you understand that? If it is, I take 2 points like this on any graph, we know gradient is m is equal to or gradient is y2 minus y1, right?
Yep.
So here y2 and y1 is same, x2
Hmm.
minus x1. I should be writing it more clearly. Y2 minus y1, x2 minus x1, and this is 0. Do you understand this?
Yep.
Okay, and what about these points here? These are actually the equation of line. Do you see this? Like the previous
Mm-hmm.
example where I made, we had this equation, or even earlier I made the equation like this, which you saw, which I made myself, y is equal to x cubed plus 2x. So this was something which gives the, okay. If you see here, so if we look at it, what is the slope or gradient on right side of this minimum point here?
It's a positive.
Yeah, it's a positive, because if I draw it would be so positive gradient, positive gradient. What about if I look at the before this minimum point? I mean, maybe if we draw a gradient which is,
It's going to be negative.
yeah, it's a negative gradient, right?
Yep.
And similarly, if we look at the other max maximum point, the previous one is a positive gradient, yeah, and
Mm-hmm.
after the point is
Negative.
negative gradient. This is something which we understand. So you should remember this. We would do some questions, but I now move to the third case. The third case is horizontal inflection. What is meant by horizontal inflection? This may happen that a curve or the equation is like this. It means normally, as I said, this could be equation with x to the power of any number. So it is not necessary that it's a parabola. Normally the parabola has the highest power 2. Do you know this?
Yep.
But it can be higher. So there could be something like this, that you have a equation and this is like this, the curve. And if you see here this point, and at this point, the what is dy upon dx at this point?
Uh,
It is again 0,
0.
because horizontal. Anywhere you have the grade, the line, like you have seen three things. What you have seen, if the gradient is like, I just move it like this, the gradient is
Uh,
positive.
Positive.
If we have like this, the
Negative.
gradient is negative. And just let me write it more clearly. Gradient negative, right? And what about if you have like this, which is horizontal? The gradient is,
0.
yeah, gradient is 0. Because rise over
Is it
run,
called
sorry,
is it called 0 or is it called neutral?
0. Why?
Ah,
y2 minus y1 over x2 minus x1. x2 minus x1. If you see, there are 2 points here and here. And if I say this is on as I showed it here, this may be, for example, 5, this may be 7. So if you see, and this may be 8. Uh, So y2 and y1 are in this example. I'm just taking this example. What is y2 here? What is the value of y2 at this point where I have put my
uh,
mouse? 8, because this is written
yep.
8. Yeah? And what is x2? I wrote it
X2 is
7.
7.
What about y1?
Y1 is 5. Y 5.
No,
No,
this
no,
is
Y1's
x
8.
8. And what is x1?
5.
Yeah, because this is x-axis. This is x-axis and this is y-axis, right?
Yep.
So if I say gradient, or I say m, so I am saying 8 minus 8, yeah, 7 minus 5.
Mm-hmm.
This comes out to be 0 divided by 2. What is 0 divided by 2?
0.
Yeah, therefore, for a horizontal line, the gradient is
0.
0. And it means dy upon dx, because we know gradient dy upon dx is the gradient, or it's the rate of change. And because it is 0, so it means there is no rate of change. And therefore we say these points as stationary points, because they are not, at that there is no rate of change. Do you understand this? Or should I repeat?
Yep, I understand.
Okay. So again, so this is important. Here the gradient is positive where I put a mouse, here it is negative, and here the gradient is 0. We don't say it neutral, we say gradient is 0,
Okay.
right? Okay, so
Yep.
look at here also. This is something which, if we have a point of, this is called horizontal inflection. So I would write it again, and I should make it, okay. So this is called horizontal inflection, horizontal inflection, horizontal inflection. So if now you look at here, what about the gradient after this point if there is a horizontal inflection?
There's a horse.
This
It's
where I am
so
putting my mouse here.
it's
Up,
it's gonna slowly increase like an
what a
exponential
gradient?
graph.
The gradient is
It's positive.
positive. We would just look at the sign. And what about here before this point of inflection? The
It's
gradient is
negative.
no. Look at the gradient again would be like this.
Oh wait, it's still positive.
Yes, still positive. So this is different than what we have been doing. Let me write it, and I would show that this is different from the one which we said earlier. So what we are saying here, let me write it in red, so because oh, I am having a little trouble getting my, yeah. So it is a gradient here, gradient positive here, and here also the gradient is positive, gradient positive. Do you see that?
Yep.
So this is different from what we have seen earlier. If there is a minima, the gradient before is, this is a minima.
Uh,
Gradient before is
before it's
where I am
uh
putting my mouse,
positive, right, negative,
negative, and after it is,
positive.
and if it is a maximum point, I mean the
Yep.
stationary point is maximum, the gradient before is
Positive,
and after is,
negative.
so you understand. Now we have something very interesting. If it is a horizontal inflection where the curve is going like this, so it is like this, it's raising, then become horizontal, and then going up. So gradient before the point of inflection is also positive, and after the point is also positive.
Positive.
So it's not changing.
Yep.
Do you see this?
Yep.
The both gradient is positive. Any question to this?
Nope.
So we would make use of these uh, things once we would be doing the, so what we would do, we would find where is the point, we would be just giving an equation, we will not have the graph, so we would take use of these facts. We would find dy by dx, then we would put a little value of x lower than that point where dy by dx is, and we would see the gradient. If the gradient is negative before and after positive, we would say this point is minima. If it is positive before and negative, we would say it's a maxima. If it is positive before that point of stationary point, and it's also gradient is positive after that stationary point, we would say it's a horizontal inflection and it is increasing. But there is another horizontal inflection that can be like this. Okay, so this was one thing. We can have even a second thing. What we can have something like here. So what it is going from, so it was going from lower to higher in this case, right?
Yep.
But in the other case, the point of inflection, the curve is like this, that it is going down, then become horizontal, and then comes down. Let's see the point of inflection in this case. What is d control z? Let me have a horizontal line. So what is dy upon dx at that point
Uh,
where I have
0.
0 because it's a horizontal, right? dy by, so I would just write it over that point. So here dy upon dx is equal to 0. What about a point before that? What would be the slope here at this point? Gradient before this point. Gradient is
Negative.
good. And what about here? Gradient is?
Negative.
Oh, this is something very interesting what we have found. If there is a gradient before the stationary point changing, so we would have these two cases. Changing means one at one it is negative and on the, so it would be either minima or a maxima. Do you understand? Here it is negative to positive, it's a minimum point. Positive to negative, it's a maximum point if they are changing. If they are not changing, at both before that stationary point have the same sign. If they have both positive gradient before the stationary and after point, it means the curve is like this. It's going from downward to upward, but is uh, in between. There is a point of inflection. Point of inflection means the curve is becoming horizontal. Do you understand that?
Yep.
And if it is before the stationary point and after the stationary point is negative, so it means the curve is coming from up to down and then becoming horizontal and then again going down. Does it make sense?
Hmm.
So we
Yep.
have four cases. If you have, so I just make them like this. So the first 2 point, the gradient before the stationary point should have different signs. In point of horizontal inflection, they will have the same signs. If they have the both positive gradient, it means the the curve is going up with the horizontal segment in between. If it both negative, it is going down with the horizontal segment in between. Do you understand all these things?
Hmm.
These 4 points.
Yep.
Okay, good. Um,
So how does the rule work? The teacher keeps on saying we need to prove using sine rule, but it's like confusing.
I would do it with you. It's not very difficult. Let's do a very simple example first. Yeah,
Yep.
and then we would, let's say, do an example. Let's say, and I would do it with your help. Y is equal to, we say the equation is a quadratic equation in the start, 6x minus 4, right? And we
Hmm.
want to find where the stationary point is and its nature, whether it's a minima, maxima, or a horizontal inflection. That's the question.
Yep.
So the question is, for this function, find the location of the stationary point and its nature. So we have two parts. First part is find,
The dy by dx.
no, yeah,
When
find
it's equal to,
find
yeah,
the
find the
location
equation.
of the stationary point.
Yep.
Location of stationary point. The second is find its
Find,
nature. Nature
yep.
means whether it's a minima, maxima, or a horizontal inflection, right? So first of all, how to do this? What do you think? We would find dy upon dx and put equal to 0. Why? Because we know at the stationary point dy upon dx or the gradient is 0. Does it make sense?
Yep.
Okay, find the dy. Can you help me to find dy upon dx? What would be the dy upon dx for the above equation?
Uh, 2x plus 6.
Okay, that's good. We've just found that dy upon dx is. And we know at point of stationary point, this 2x plus 6 should be equal to 0.
0.
So this means, can you tell me what is x then equal to?
3.
No.
-3, -3.
Yeah, -3. So x is negative. So we found that this is the -3. Now we are confused whether it's a minimum, maximum, or the point of inflection.
Yep.
So I would just move back to where we did this earlier. We said we would check the gradient sign only. We are not very concerned about their value. We would just be concerned about the gradient. So sign. And the gradient is given by what? This was the gradient, right? dy upon dx, which you helped me to write. That was
Hmm.
2x plus 6, right? Okay, let's do that. So we have x is equal to -3. So I just plot it like this, just for a clarification. Otherwise, it's not required. This is a point. So what we said, we want to check the sign just before this of the gradient. So it means any point here on the x-axis, or we have to check some point, sorry, some point. Are you with me
Yep.
here? So what does it mean? What we would do? We know dy upon dx is our gradient. So we want to check first the point right side of the or left side, which you would prefer. So our actual point is this dy upon x is equal to
Hmm.
-3. So we would be checking 2 points, one on the right side and one on the left side.
Left.
So which one you would like to check? On the right side or left side? First,
Right.
right. So it means we can put x is equal to any number which is more than -3. What you would like to put? For example, can we put -2.5
Uh,
or 2.8 maybe?
-2. Would that be easier?
No, that is going a lot away. That is good, but we would normally prefer to take a point which is near. So this was x is equal to -3. You understand? Because we found this. So we would just say, let's put x is equal to -2.8, because that would be, so I say this is x is equal to -2.8. We want to be near it. You can put even -2.9. Yes?
Yep.
And where you have to put? Can you help me to write?
Uh, so you put 2.9 and substitute it instead of x.
Yeah, so it would be 2 times. We took 2.98. So should I take
Uh,
2.9, or you are happy with 2 point, -2.8?
2.8. Yeah,
Okay,
2.8.
-2.8 plus 6, right?
Yep.
What does this mean? 2 times 2.8 is minus
Uh,
2.8 is
yep.
minus 5.6 plus 6. So it means
So
what is the sign? This is
0.4.
positive.
Yep.
Yeah, because it would be 0.4, which is positive, right?
Yep.
Okay, so it means we see it would have a gradient like how much? Positive is like this. Do you remember? Positive is like this. So we say after this point it is going like positive. I put another color instead of. So we would say after this is x is equal to -3, right? And we saw this is positive, so this is like this. Do you see this?
Mm-hmm.
So can you help me now to write dy upon dx on the left side? So what x I should put?
3 -3.1.
Very nice. So can you do this for me? 2 times -3.1 plus 6. So this is equal to minus 6.2 plus 6, and this is minus 0.2. So it means this tells us on the left side we have a negative gradient. So it would be something like this. Do you see this? Negative gradient, because we know positive gradient is like this and the negative gradient is something like this. Do you see this or no?
I do. Yep.
So it means we have something like this. So what is x is equal to -3? Is it a maximum or minima or a horizontal inflection? Because we see it has a it has a it has a negative. gradient here and a positive gradient here. So I take a positive. So can you tell me, is it a minima, maximum, or a horizontal inflection?
It's a maximum.
If it is like this, is it a maximum or a minimum?
It's a minimum.
Yeah, it's a minimum. It is a minimum. Do you understand this or no?
Yep. Yep.
Does it make sense to you or no?
It does.
So, so what is the minimum turning point at the moment? Can you tell me what is the minimum turning point? Turning point, this is called also the turning point. Why? Because it goes and then, so this is, can you tell me what is the minimum, what is the turning point, minimum, and this was a turning point. It could be minimum or maximum, and we found that this is minimum.
Minimum.
So can you tell me what is the minimum turning point?
Uh, when x is equals to -3.
Yeah, so we put in that equation
Yep.
where we will put,
The original equation,
yeah,
which
which x
is
squared plus 6x
yep.
minus 4. So we would put y at x is equal to -3, which was actually our equation was x squared plus 6x minus 4. So we would put, this would become, this is equal to -3 square plus 6 times -3 minus 4. Can you calculate and let me know what is the values?
Yep. -3 squared plus 6 brackets -3 minus 4 is equal to -13.
Yeah. Negative 13. So it becomes negative 13, right?
Yep.
So if it is, so what we have now, something we saw that whatsoever the equation is, the
Mm-hmm.
minima is actually at minus 3 comma minus 13. So if I say 1, 2, 3, and I have to go down maybe a lot, so I just assume that this
Yep.
is minus 13. So we see that this is here, it is going like this.
Mm-hmm.
And then you can even find where it cuts the,
X-axis.
how you find that?
When y equals to 0.
Yeah, so we had a x square plus 6x minus 4 is equal to 0, which was, so can you find what is, this has now become a quadratic equation.
Uh,
Or you can use the, which is the roots of a quadratic equation, do you know? Minus b plus minus b square minus 4ac whole under root divided by 2a. Do you know this?
yep.
So if we do quickly, so the roots would be minus 6 plus minus, what is b square? 36 minus 4 times a is, what is a?
A is 1.
1. And what is c?
C is -4.
Negative 4. And whole divided by 2 times a is 1, right? So this comes out to be minus 6 plus minus 36. And what next?
And
If you multiply the other one, minus 4 inside
times
the under root, what is that?
-4 equals to +16.
Plus 16 divided by 2. So this comes out to be minus 6 plus minus 36 plus 16 is
52.
52 over 2. So you would take your calculator to find what is 52 under root, and then so this would become two equation, minus 6 plus 52 under root divided by 2, and second is minus 6 minus under root 52 divided by 2. Can you
Yep.
give me the values?
0.6055.
0.6055. What about the next?
Uh,
Yeah,
-6.6055.
6055. Yeah. So we understand. What we understand, if you go back to this, this is going somewhere. If it is 1, it is here that it would go like this. And here 1, 2, 3, 4, 5, and 6. I am just rubbing this, and this is our minimum point, and I would do it like, because previously we were not having the information 1, 2, 3, 4, 5, 6, and here this would be something like, sorry, Control Z, and it is something like here. This is, so it would go something like this. Do you understand this?
Yep.
We found these two, and we can also find what is this point. This point would be once x is equal to 0. This would be y is equal to -4. So this is not 2, this is here -4. Do you understand why y -4?
Mm-hmm.
Why? This was
Uh,
our original equation, x squared plus 6x minus 4. So we put x is equal to 0 because we want to know the y-intercept, and it has only y-intercept 1, so
yep.
-4. So we are able to draw this, and this is going like this, and this is going like this. So this is the equation. This is the, so we had just the equation. We are able to find the parabola and plot it.
Yep.
Does it make sense to you?
Yep.